This is an example of an AC node solutions tutorial in Circuit Tutor at level 1. So we're going to go ahead and go into AC node solutions. And as always, we have examples available at several different levels of difficulty. And it's usually a good idea to view some of those examples before starting the exercise to get an idea of how to do it. In this case, however, I'm going to skip directly into the exercise at the easy or level 1. So our first task, as always, when doing nodal analysis, is to pick a reference node. If we fail to pick a reference node, we would be unable to calculate any of the node voltages because everything would be relative. So generally we want to place this on something that will have connections to a lot of circuit elements to minimize the complexity of the equations, and also to any voltage sources that are present. There are no voltage sources here, so clearly the black node is connected to 1, 2, 3, 4, 5, 6 elements as opposed to only 4 elements for the other two nodes, so it would be by far the best. So we'll place it there, and that will again simplify the equations as much as possible, which is certainly a good thing to do. Here are the written instructions. If you need those, you can review them. And if you ever need to re-review those, you can always go to the help menu here and pull those back up. Okay, so because this is a solutions game, we are being given the KCL equations, and we do not need to enter those. But for this level, we do need to enter the SOT variable equation for the unknown voltage V0. Since that is a SOT branch voltage, it appears across a single element. Therefore, we'll select SOT branch voltage from the menu, and that'll be V0 equal to, and now we observe that that's actually the voltage difference between V2 and V1. So it's a difference in node voltages, so we need this term. And the voltage on the positive side is V2, so we enter 2 there. And on the negative side, it's V1. So it'll be V2 minus V1 will be equal to V0 because of the defined polarity of that voltage. So now we check that equation, and that is correct. And now we've written all of the required equations for this circuit. So we just click No More Equations. And now we have to do the new part in the solution tutorial, which is to combine the coefficients of the KCL equations into a standard form in preparation for actually solving those equations. We're not going to use the SOT variable equation at this time. That'll be used later. Now, we are permitted to multiply through by a constant. For example, if you wanted to rationalize terms, maybe by multiplying through by, say, in this case, the common denominator, I guess, would be 90. You could do that, and that is allowed. You're not, however, allowed to make linear combinations, such as adding this equation to this one or making any substitutions, which don't apply here but might apply in other problems. Okay, so now we're going to look for the coefficients of each variable in this equation. So when we look for the first equation, for the coefficients of V1, we find 1/5, or 0.2, and then we find 1/2 added to that, and 0.5 and 0.2 then are 0.7. And then there's another term, but that will be imaginary because of the j. So I'm going to enter 0.7 first. That's the real part. And I can compute this really in my head also because 1 over j9, well, we know that 1 over 9 is 0.1111. It's a repeating decimal, as in any number of ninths would be. And 1 over j, that's actually very simple to compute because 1 over j is always negative j. And the reason is simply that j squared is by definition negative 1. So 1 over j is negative j. And remember that we do have to take the reciprocal of both numbers here. Sometimes people make the mistake of taking the reciprocal of the j and then forgetting to take the reciprocal of the 9. But that would be incorrect because the reciprocal applies to both of these numbers in the denominator. So this is going to be negative j times 0.1111. And I'll enter 4 significant digits there at least to ensure accuracy, especially when we're working with complex numbers. That's very important. Okay, then the coefficient of V2 in this equation, I just have a negative 1/2 or negative 0.5. And then the constant term, I have to add this to both sides to bring the constant over to the right-hand side. All the rest are coefficients of variables. And so that will give me 1 angle 180 degrees. Oops, not 10, 1. Now, you may know that one angle 180 degrees, if you think about the Argand diagram, that's actually just -1 in rectangular form. But here I'm being required to enter it in polar form, and I'm not allowed to enter a negative number for the magnitude of a complex number because magnitudes are never negative. So if I put a negative sign there, for example, you'll see it tells you there's an error and it tells you, it has to be real and positive. And if you wanted to form the negative of a complex number, you change the phase angle by 180 degrees, plus or minus 180. So I'll get rid of that negative sign then. And for the second equation now, again, I look for the coefficient of v1, and I see that that will again be just -1/2. That's the only term. It has v1, so -0.5. And then for v2, I have 1/2 or 0.5, and then this one's going to be imaginary, and this was 1/7, and you may or may not remember that that's 0.1429 in decimal form to 4 digits. So I'm going to add that to 0.5, and that will give me 0.6429. And then for the constant term, I have to add 1 to both sides here, 1 angle 0. And so that just becomes 1 angle 0 here. And that would be my constant. And now I'll just check the equations. And it looks like I did make a mistake there. So that, again, is... Oh, I forgot the imaginary part of v2. I meant to enter that, and I just forgot to do that. So that was the real part only, but I also have the imaginary term. And remember that 1 over -j is j, and then the 1 over 2 is 0.5. So this needed to be plus 0.5j. So again, you have to remember to put in both the real and the imaginary parts. That's a good illustration of what can go wrong if you don't. Okay, so that is correct. And now the simplified equations have been printed here for reference. The next step is to form these into a matrix equation. And that's actually very easy to do because it gives us a button where we can just copy those from the simplified equations. We don't really have to retype those. And remember what that means is that this times this is equal to this. This times this plus this times this is equal to this. That's our first simplified equation, as you can verify. And then the second row in the matrix just means that this times this is equal to this times this, and that gives us the second constant. So that's equivalent to those two equations. So we'll check that, and that is correct. Now the next step is going to be to actually solve for the variables v1 and v2. And remember, our SOT voltage involves both of those, so we will need to compute both of those values. Now, before we do that, there's a variety of ways, and sometimes people wonder, well, how do you solve a system of algebraic equations that has complex numbers? Many people have never done that before. So the answer is you do it exactly the same way you would do it as if they were real numbers. The only difference is now you're handling complex numbers as the coefficients, and so you would just treat that the same way you would treat a real number. You can multiply it, divide it, add, subtract as you need to. And you simply do the arithmetic on a calculator, typically, that can handle complex numbers. So the arithmetic is a bit more involved, certainly, but the principle of solving algebraically with complex number coefficients in an equation is exactly the same as when you do it with real numbers, and so everything you learned in elementary algebra still applies. And for a 2x2 system, honestly, it's almost silly to use a matrix. If it were larger, it might make sense to do that. But for all the problems in Circuit Tutor, they're typically going to have only 2 KCL or KVL equations, and the other equations are usually simple enough that they can be substituted into those and just keep it as a 2x2. So it's rarely necessary to go to a full-fledged Gaussian elimination for the problems that we're going to give you here. Okay, now, so we're going to just use elementary algebra to solve these. Now, your instructor may ask you to turn in a written record of your work in doing this. If so, then you should keep that. And it may be a good idea to keep that for your own purposes when you're studying anyway, just so you can remind yourself how to do that complex algebra. So it's usually a good idea to keep a well-organized copy of your work. Okay, so now we need to go ahead and actually solve these for v1 and v2. And again, I'm just going to use this. So I'm going to do that algebra on paper. And so what I've done here is I've just copied over these two equations, the 0.7 minus j, 0.11v1, and I put a little bar over there just to indicate that that's a complex number. I suppose you don't really have to, but it helps to remember that. Minus 0.5 V2 is equal to 1 angle 180. And remember I said that that was -1, so I'm just going to write it here for simplicity as -1. And then the second equation is minus 0.5 V1 plus the 0.6429 plus J.5 V2 bar is equal to then 1 angle 0. I can just write that more simply as 1. So there's a variety of ways now I could solve these two simultaneous equations in V1 and V2. Looks like that one's missing the bar, but it should be there. And for example, you could solve this first equation for V1 bar. For example, add this to both sides of the equation, and then just divide by the coefficient of V1 bar. And that would give you V1 bar in terms of V2 bar. You could then substitute that in here, and that would just give you a single equation in V2 bar. And again, just do the arithmetic like you would normally do to solve for V2 bar, and that would give you an answer. And then you could solve it back and plug it back into either equation to find V1 bar. You could also solve this for V2 bar similarly and plug in here, or you could solve this equation for either of its variables and plug it in up here. I mean, you can do it however you want. The method I'm going to illustrate here is maybe a little bit more systematic. It's just going to multiply the second equation by a constant. In this case, you see it's a complex valued constant. And the purpose here is to basically make this first term such that I can subtract it from this and have all the V1s go away, which is more or less equivalent to doing the substitution method, but it's just the way I like to do it. So what do I have to multiply that? Well, I want to get this when I'm done, so I have that in the numerator, and then I divide by this coefficient. And so obviously when I multiply this times this, that's just going to give me this, because the other two things cancel out, and that's what I have here. So then if I subtract the two equations, that will cancel out the V1 term, and I'll have nothing but a V2 term, which is what I'm doing here. And I, of course, have to do the same thing with the other two terms in the equation. As you know, when you multiply an equation by a constant, you have to multiply every term in the equation by the same constant. So that's what I'm doing here schematically. Okay, so let's go ahead and subtract these equations now. Just drawing a line here to indicate the subtraction. And the V1 terms we already know we're going to cancel out, so we have nothing there. But for V2, I first have negative 0.5 V2 bar, and I've factored out the V2 bar here, so just negative 0.5. Then I have this coefficient that's copied there. And remember, that multiplies now this other coefficient, the 0.7 minus J 0.11111, divided by the negative 0.5. And remember, I'm subtracting that now because I'm doing subtraction. And so that's what I have there. And then on the right-hand side, I have -1, just copies down here, and then subtracting 1 times this constant. So, of course, the 1 goes away, and it's just minus that constant, basically. And since there's a negative sign in the denominator, I'm just canceling that with the minus sign here to make it a plus, just to simplify a little bit. So now, this is where I'd probably want to break out my calculator. So I'm going to pull up a calculator emulator here for a TI 84 Plus specifically, but this will be very similar to what you would do on any TI 83, 84 model if you happen to have those. At TI 89, it'll be similar, although it actually be a little bit easier because it handles complex numbers better on an 89 as far as the rectangular and polar mode is concerned. And if you have some other model, well, the procedure would be broadly similar, but you'd have to look in the manual for that model. Okay, so let's go ahead, for example, and evaluate the right-hand side here. So that's quite simple. I just write -1, and then I'm going to add, and now I'll put this in parentheses, 0.7 minus, and remember J is written as I in the calculator, so that's above the decimal point key here, but using the second. Okay, that seems to have done something funny there, so I think I clicked the wrong button there. So second I, yes, I clicked the green button by mistake. So that's I 0.111, close parentheses, divided by 0.5. And that should be the complete expression, so I just click enter. and that will give me this number I've written here, the 0.4576 rounded to 4 digits. And again, it's good to carry along at least 4 digits in everything in doing complex numbers to avoid round-off error, because it's very easy to get round-off error with complex numbers. And then the angle is going to be, since I'm in the degree mode, it's negative 29.05 degrees. Now, I should have pointed out at the start that you have to be in a complex number mode in order to do what I just did. If you did that in the real number mode, you would not get a correct answer at all. So you always have to check that you are, in fact, in a complex number mode. And I also put it in degree mode because I want my answer typically in degrees. Now, I could have also put it in rectangular mode for this purpose. Since it's an intermediate value, I don't really care which form it's in. And maybe it's even easier sometimes to enter a rectangular number. But if you wanted to change the mode, you just go here and again go down to this line, and then you select either the rectangular or the polar mode as appropriate. And again, you can change your angle here, but normally we want to use degrees. Okay, so that's that value, and then I would do a similar calculation for this. It's straightforward, so I'm not going to illustrate that in detail here. But basically that would give us 0.7561, angle 47.46 degrees for the coefficient of V2. And then I'm just going to take my answer here and divide that by this coefficient. So I'm going to put that in as 0.7561. But I forgot, however, I need parentheses here. So let me put in parentheses first, because again, I'm going to have two things multiplying each other. If I didn't use parentheses, then I would actually be multiplying by the second part rather than dividing by it as I should be. So again, that would be 0.7561. And then I'm going to use this trick of this variable e that I've already defined. And that's because of the peculiarities of this calculator. I define that to be lowercase e to the I pi divided by 180. So that when I raise that to the power of this angle in degrees, which is going to be the 47.46, then it will effectively be converting that to radians, which is the only angle mode you can use here when you're entering a complex exponential on this type of calculator, unfortunately. Okay, so we have that, close parentheses, enter that, and that would give us our value here for V2 bar of 0.6052 to 4 digits, angle negative 76.51 degrees, and the units there would be volts. Then I would go ahead and now I need to find V1 as well, because I needed the difference of those two numbers for my SOT variable. So I can take either one of these two equations and plug in V2 bar and solve for V1. So I've chosen to, let's see, do this one. So we have basically taken the V1, it's going to be equal to this times the V2, which is the thing I just calculated. And then I'm going to subtract 1 from that, bring the 1 over here, and bring the 0.5 V1 over here, and then divide by 0.5, or in other words, multiply by 2 to get the V1. Okay, so this expression, again, I'm not going to go through the step of entering that in the calculator here, but it would be similar to what I did in these other examples. And that works out to 1.3755, angle negative 153.4 degrees, and also in volts. So now I'm going to go ahead into the Circuit Tutor window and enter those values here. So I have V1 is 1.3755, and then the angle is negative 153.4 degrees. And for V2, then that was 0.66052 and negative 76.51 degrees. And just double check those. That looks good. So check those, and indeed those are correct. Okay, so then the next step would be to use our SOT variable equation to actually compute the SOT variable. And so now we just have to take V2 minus V1, and again that would just be a matter of taking those two numbers on the calculator and subtracting them using the methods that I already showed you. So I'm just going to put that in here quickly. And that works out on a calculator to 1.371, angle 1.132 degrees approximately. And so we'll check that. And that is correct. And finally, the last step here would be to do an inverse phasor transform. In other words, to put this value of V naught into the time domain. So let's go full screen to do that. And so now I'm going to be using basically this value V naught bar, which has been, or V naught rather, which has been printed here. I will need my omega. And remember, whatever multiplies t by definition is omega, not f. It's omega. It's the angular time frequency, because it has to be, radians per second times seconds will give us radians, which is the normal argument or unit that the argument of a cosine should be in. So I put in a number that's 30 kiloradians per second, so I have to enter that as 30,000. This does not accept metric prefixes in this particular text box. Okay, and then the phase angle here of the V naught is 1.132 degrees. I'll just enter that as 1.13 should be sufficient. And then the magnitude would be the 1.371. And we'll enter that. And that is correct. That does complete that problem, and if you wanted to get a detailed explanation, for example, of the KCL equations and how the SOT variable equation is derived, then you can request that, and it will show you some more details about that and show you how the different current factors are derived. You can even get a very detailed explanation here if you want to click this button. And that basically concludes that problem.